Hello and welcome! In this lecture we're going to learn about one very crucial thing, adding some pathfinding so our units can detect obstacles and walk around them. The specific algorithm we're going to implement here is called A-star pathfinding. In this first lecture we're going to go through the theory of how the algorithm works, and after that we're going to implement it. So our goal is to have our grid, then some positions are walkable and some are unwalkable. Then the algorithm will be able to calculate a path towards the target point and output a list of grid positions. And then our move action will move the unit along these grid positions. So before we actually get to the code, let's first check out the theory. Now here I should point out that if you're using pathfinding in your own games, you should probably use a proper asset. The reason for that is because, while it's relatively easy to implement and get it working, it's actually quite a bit more difficult to make it work well and very performant. Although in this case, since we're making a turn-based game, in this kind of genre performance isn't that important. Basically waiting 1 second to calculate the path isn't going to be game-breaking, whereas it would be in some kind of real-time game. So like I said, ideally you would want to use a proper asset that has been well made and is very performant, but since this is a teaching course, over here let me teach you how the algorithm works. Now the goal of the A-star pathfinding is to find a path going from A to B. The map is grid-based and we can move in all 8 directions. Now each node is going to have 3 values. First up we have the G cost. This one is the walking cost from the start node onto this node. So for example, if our start node is 10, then moving from 10 to this one on the right has a cost of 10, and moving from this position to this one has a cost of 14. Now as to why these numbers, now actually going to the right we would give that a cost of 1, and then going diagonally, the math for that is one side then another side, so that would be 1 plus 1, and the square root of that, which would be 1.4. So the reason why we have these numbers is just so we work with ints instead of floats. So instead of 1 here and 1.4 here, we've got 10 and 14. So again, that's the G cost. It's the walking cost from the start node onto this node. And when I say this node, I mean the current node that the algorithm is searching. Then the next one we have is the age. This one is the heuristic cost to reach the end node. So this is essentially a very rough estimate to try to reach our goal. In our calculation, we're simply going to assume there are no walls anywhere, so we're going to try moving directly straight towards the target. So in our case, if we're going from A to B, then for our heuristic, we're simply going to try going directly from here and here. Again, this is just a very rough basic guess, just to figure out which nodes to prioritize. And finally, we have the F, and the F is simply G plus H. So this combines the actual cost going from the start node to the current node, as well as an estimate to reach a target goal. Using this, we can prioritize nodes with lower Fs, since those are more likely to be closer to the goal. Then we just keep searching all of our nodes, and the algorithm stops when the node that we are currently testing is already the goal node. So in this example, this is A and this is B. You can see how the G is constantly increasing. Again, the G is the actual walking cost from the start node. And the age, which is the heuristic, you can see it's constantly decreasing. So we're constantly testing the nodes with the lower F in order to prioritize which ones to search next. So for example, if we start over here in A, we're going to search for the neighbors. So we're going to search this node, and this node. Now these two are unwalkable, so we're going to ignore them. So we go from this node into this node. Then over here, we can try moving into this. Once again, this one is unwalkable, so we ignore it. Then we check the F cost for both of these. And from these two, we're going to prioritize this one because it has a lower H. So then we're on this node, so we test this one, and this one. And one of the ones that we're going to test is the final node, so there we've reached the goal. Like I said, the algorithm stops when the node that we are currently testing is also the goal node, so we stop here. And then we basically trace the path back from the final node onto the start node. So each node knows the previous node that it took to get there. So this node would have a pointer to this one, this one to this one, this one to this one, and here we have our final path. Then the algorithm, we also have two lists of nodes. We have the open and the closed list. The open list are all the nodes that we still have yet to search, and the closed list, these are all the nodes that we have already searched. So we're going to keep going until either the current node is the final node and we've reached the end, or the open list is empty, which means there is no path to this goal. Alright, so this is the theory behind the A-star algorithm. It looks a bit complex at first, but it's actually quite simple. If you want, you can rewatch this video if you're a bit confused. And when you're confident that you understand the theory, then let's keep going on to the next lecture and start implementing the code.